I am the nature hacker, and this is your world. Today I want to talk about rockets in space again. This is the 5th video in the series, so if you've missed the other 4, you might want to check those out, especially videos 3 and 4. I feel those are probably my best ones on this topic. So this time around I wanted to talk about more of the physics of what is going on inside the rocket nozzle, inside the combustion chamber of the rocket nozzle, and the, well, I guess chemistry of that as far as gas law and things like that. So in videos 3 and 4 I talked about joule-free expansion and how when exposed to a vacuum, a gas will expand at its maximum possible rate, and it will not be able to do work. So it will not be able to push the rocket forward. It's just going to just get sucked off into space, for lack of a better word, and it's not going to actually be able to sustain a reactionary force according to Newton's third law. So I want to take a closer look at inside the chamber, and I want to help to explain the chemistry of what's going on. So as far as gas is concerned, we have a few equations that I want to point out, and that is PV equals nRT, P equals pressure equals, force equals pressure times area, and work equals pressure times area times the length of displacement. A guy named Christopher Partridge brought that last one to my mind, so I just want to thank him. I'm sure he will be commenting on this video. He's commented on the other ones. So let's start with that first equation, PV equals nRT. So what does this mean? Well, it means that pressure times volume is proportional to temperature. That means that the pressure in a tank varies basically only on volume of the tank and the temperature of the gas. Okay, as long as we have an ideal gas, which under this circumstance, under almost any circumstance, gases can be modeled as ideal. If you want to say that if a gas is not perfectly ideal, we can't apply equations to it, then you know what? Time to throw out all of chemistry, because all of chemistry is based on the ideal gas law. So let's just accept that these are, first of all, close enough to being ideal, and not only that, this is the most close to ideal situation as possible in the entire world. A gas exposed to a vacuum is the most ideal conditions for a gas ever, because when a gas is not ideal is when it's super high pressurized, where the particles are interacting, their particles' interaction with each other is negligible. But when a gas is exposed to a vacuum, the pressure is extremely low, and we can neglect the particles interacting with each other. Hence, it's an ideal gas. Alright, so people saying, oh, well, it's not an ideal gas, so we can't talk about joule-free expansion or whatever ideal gas, things that require ideal gas. But come on, if you're going to say that we can't look at something if it's not 100% perfect ideal gas, then time to throw out all of your chemistry textbooks, because nothing is 100% perfectly ideal. Alright, so PV equals nRT, pressure times volume equals temperature is basically what that's saying. N and R are just constants depending on the gas and the moles of gas, things like that. So but basically it's just pressure equals volume, pressure times volume equals temperature. So what this means is that in the combustion chamber, as long as the volume is constant and as long as the temperature is constant in the tank, that means the pressure is constant. So what this means is if you open up the tank, which obviously a rocket engine does, the gas will distribute itself into the tank equally. So just because you open part of the tank does not mean there's going to be an imbalance of forces. There is going to be no imbalance of forces. The reason is because the pressure in the tank is going to be a set value. According to p.v equals nRT, every part of the tank is going to have the same pressure. You know, does p.v equal nRT say that the front of the tank is going to have a higher pressure than the back? No. p.v equals nRT means that the pressure at any point inside that tank is going to be exactly the same. That means that the pressure at the hole that you make in the tank is going to be the same as the pressure at the front of the tank. So you can't say there's an imbalance of forces, that there's a higher pressure at the forward part of the tank, which pushes the tank or the rocket forward. You know, that's NASA's claim. I mean, they have, it's funny because they have so many different ways to explain how rockets work. They're like, oh yeah, the gas pushes on the nozzle. Oh wait, no. Another theory is that the gas pushes on the inside of the tank. Wait, also just the force, just the equal and opposite reaction. Or that the gas pushes on the cloud. You know, they make up all these different things. They're all different explanations of how rockets work. So obviously NASA's just scrambling for explanations that are going to, try to, make sense to brainwash people. So anyway, p.v equals nRT means that every part in the tank, whether it's the hole in the tank or whether it's the front of the tank, is going to have the same pressure. So there is no imbalance of pressures. The pressure is equally distributed throughout the tank, and that makes sense because these gas particles are moving so fast that there is not going to be any pressure imbalance possible. It's just going to remix, instantly remix and create a constant pressure throughout the tank. So the next equation is force equals pressure times area. So this just means that since the pressure, so the first equation told us that the pressure is equal throughout the tank. Every part of the tank, the pressure is equal. Now this equation says that the force at any part of the tank is equal to the pressure times the area. This is also pointing to what we are saying, and that is that that since the pressure is equal throughout the tank, the force on any given piece of that tank is going to be the same throughout. Whether or not the piece is the tank or not, I mean, it's hard to figure out how to say this. If you look at any little piece of the tank, whether the top of the tank or the side of the tank, the bottom of the tank, even a hole in the tank. If the hole is the same size as a piece of the tank over here, there's going to be an equal force on that. So on the hole at the back of the tank, there's going to be a given force pushing out through that hole, right? But at the front of the tank, at the same cross-sectional area, you're going to also have an equal force there. So that means there is no force imbalance. All the forces are balanced. The same force that's at the back of the tank is the same force that's at the front of the tank. So that means that the tank is not going to move. If there's a total force balance, the tank will not move. The force on the left side of the tank on this cross-sectional area is the same as the force on the right side of the tank at this cross-sectional area. So obviously the tank isn't going to move side to side, is it? No. And the same with the front and the back. The force at this area at the front is the same as the force at this area at the back. There's no net force. They cancel each other out. There's going to be no motion. I hope that makes sense. I mean, some people might probably be thinking, well, the forces are the same, so it's equal and opposite. Okay, yeah, it's equal and opposite, but you have a force going this way at, let's say, 100 newtons. You have a force going this way at 100 newtons. Are you going to get a motion? No, you're not going to get motion. You know, if you've taken statics and you can draw a free body diagram, draw a free body diagram of the tank. You know, let's say here's the tank right here. You got a force of 100 newtons that way, and you have a force of 100 newtons that way. Is the tank going to move? The tank is not going to move. It's the same, you know, if you have 100 newtons up and 100 newtons down, it's not going to move. So, so that is force equals pressure times area. Now, the the equation that Chris brought up was that work, he said force, but he meant work. Work equals pressure times area times the length of displacement. So, what that means is that, you know, basically another thing, you know, obviously what they say is that the imbalance of forces pushes the rocket forward. But according to this equation, there can be no work done. Alright, so let's take a look at this. I mean, this equation might actually be a little harder to explain because you could use it to fool people into thinking, you know, NASA rocket theory. So, when you have your gas in your chamber and it expels out the back, you know, you have a work done, but work is only done when you are moving and something. So in order for expelling gas to do work, you have to be pushing something. I mean, that's just the way it is. You know, if I'm exerting a force against a rock and the rock is not moving, am I doing any work? No, I'm not doing any work. I'm only doing work when the rock starts to move. Even if I'm applying a force, I'm not doing work until the rock starts to move. So it's the same with a gas in the nozzle. So you have a gas in the combustion chamber, and so in order for that gas to do work, it has to push something. Just like me pushing the rock, I'm not doing work until the rock moves. So if we're expelling gas out, for the expelled gas to do work, it has to be pushing something, just like that rock or the bullet or whatever. You have to be pushing something out. And in a rocket's case, you're pushing against the atmosphere. You're pushing against that 14.7 psi to do work. If there's nothing to push, guess how much work you're doing? Zero work. So that is how to think about that equation. I mean, you could be tempted to think, oh, well, the thing that we're pushing is the rocket forward. We're pushing the rocket forward to do work. Well, in order to push, I mean, for the gas, okay, look, you can't just randomly push the rocket forward, just randomly, okay? You have to push it forward. And in order to push it forward, you have to do work. So the gas has to do work to push the rocket forward. And in order to do work, it has to push something else backwards. Okay, that's the equal and opposite. That's Newton's third law. You know, so you can't just push something forward because you're with mind control or something. You know, you have to do work in the opposite direction to produce work in the forward direction. If the gas is not contained and it's pushing on nothing, the gas is doing no work. Alright, so that's a little more in this Rockets Don't Work in Space Theory. Check out my website, naturehackerproducts.com. I will link to it in the description. I have a forum there so we can discuss there easier than YouTube comments. And I will see you there. I am the Nature Hacker. Do work.